शीजा 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 मुझे फोन चाहिए जल्दी जल्दी मुझे फोन चाहिए वापस आना था ना जरूरत पड़ती है कभी और चार्जर भी वो चल ही नहीं रहा हाँ जी खाला को बोलो वो क्लास के बाद आएगी वहीं पावर ऑफ कर उसको तभी मेरा व्हाट्सएप नहीं कनेक्ट हो रहा है अजीब ही बच्चे हो आप पता नहीं क्या आपने खुराफाती दिमाग से सोचते हो फिर पता नहीं क्या करते हो Okay, am I audible? Just raise your hands.
Yes, mom.
Okay. Just a second. Okay, so were we had touched the topic of the big O and omega. Those are known as asymptotic notations. So we'll go over them in a bit of detail in this lecture. So let me. Okay. So there are, like I said, there are three main notations. They're known as asymptotic notations. The three main ones are omega, big O, and theta. And the converse or the opposite of them, or the smaller versions, which we say, are the small o and small omega. So what is basically asymptotic notations? We want to define the runtime of an algorithm with some mathematical functions. Why we need mathematical functions? Because we need to be able to write a program and then say that for particular size of input, or if you have to deal with this amount of data, this is the amount of time it will take. We usually, like I said, we talk about the amount of time taken in the worst case. So we always give them the worst case time analysis, which is the upper bound that your program will not take more than this amount of time in any case. Okay, so that is why we want to use some mathematics to tell this in terms of numbers and time. So we, like I said, we have to use the worst case time. So these asymptotic notations, they are expressed using the highest order term in the expression. I will come to that in a while. So if your function runtime, like I said, if you have a double for loop, you have a single for loop, you have consecutive statements. So you will have, let's say, n square plus n plus 1. So we will take the highest order term. I'll tell you why we do that in as we discuss this in a while. Okay. So these are the 5 notations we will see. Mostly you will see that we use either theta or big O. We do not use omega, small o, and small omega in most of the cases, because we usually want to tell the user that your runtime is less than this particular function. So for that we use big O, or your runtime is equal to, almost equal here doesn't mean exactly equal by decimal values. It means equal as in it is in this range. So we have this, these are standard functions that are defined to compare two function sizes. So you write your function, you write your program, you calculate its runtime based on what you are using, recursion, loops, and then you get a equation, mathematical, and then using, I want at the end of the course you should be able to see that equation and tell me whether it's O of n square, O of log n, what your program runtime is. Okay, so what this runtime is defined in terms of functions, so that you can tell the user that as you give input, as your size of input increases, how does it affect the efficiency of your program. This is how mathematically
I can tell you using a graph, plot a graph to show you how the time will change based on the size of your input. So we are actually telling the rate of growth of the functions. Okay, so now coming to the big O notation, this is the formal mathematical definition of this big O. Okay, I'll just read it out once. For function gn, we define O of gn, or we say big O of n, as the set. So the set definition is O of gn is equal to fn. That means there exists positive constants c and n0 such that for all n greater than n0, which I showed you in the graph last time, we have this equation true: 0 less than fn less than cgn. So basically, if you see this, this is what your big O notation describes. So if you're given two functions, fn and gn, if you see fn in the graph lies below gn, and it lies below gn, and you can see a constant c. So if you tell me that fn is less than, or fn is O of gn, that means fn is less than or equal to gn. Less than means the rate of growth of fn is less than the rate of growth of gn. So if you see the two graphs, the line of fn lies below gn. So fn grows, definitely it grows, but it grows at a slower rate than gn. And if you see at the beginning, you see the graph goes up and down. Amandeep, are you there? Amandeep, are you there?
Yes, ma'am.
Yeah, I made you the host. If you see anybody in the list who does not belong to the class, just take them. I mean, just exit them from the meeting. Okay?
Okay, ma'am. Okay.
So, okay, just can you give me rights to screen share? Not video, screen sharing.
Screen sharing option.
I actually I could not figure out where to give the co-host option.
There is no option for, screen sharing.
Okay, just a second, let me. Okay. Okay, then you can just scan through the list. If you see somebody, then just message me. Give me the name.
Okay, ma'am.
You have to make me the host again.
Yes, ma'am. I did. I have removed one who was not from our class.
Okay. Yeah, if you see somebody, just send me a message. I'll remove.
Okay, ma'am.
Okay. So, okay. So we are here. Let me just use the whiteboard for some time to explain this graph. So if you see, the graph is like this. This is your Fn and this is your Gn. Some constant into Gn. If you see, this one is N0. So before N0 in this time frame, when N was between 0 to N0, you see the relationship between Fn and Gn is not definite. Sometimes Fn is greater than Gn and sometimes Fn is less than Gn. But after N0, you see a constant pattern where Gn grows at a faster rate than Fn. That is why this N0 is important. This tells you that beyond this point, this is how your functions are going to behave with respect to each other. Okay, so this is your 0 here. So the rate of growth of Gn is greater than the rate of growth of Fn. So you can write Fn is O of Gn, which is to understand it, that's how you can remember. It is the less than or equal to. Equal to point is here, where for N0 both are at the same. The value of both Fn and Gn is same. But other than that, beyond N0, Fn is less than Gn. So if that is the case, we say Fn is O of Gn, which means the rate of growth of Fn is less than the rate of growth of Gn. Okay, so this is your big O. You'll see that omega is the flip of this. You'll see Fn, here Fn is less than or equal to Gn. If you want to determine the relationship between the two with Gn on the left hand side, obviously Gn is greater than or equal to Fn. So that will be your omega notation. We'll just show you that on the graph here in the presentation. So this is your big O notation. If you see, there's a small note on the left hand side of the slide. It says Fn is theta of Gn. If, for example, we haven't got to theta, but just to tell you, like I said, big O is less than or equal to, omega is greater than or equal to, and theta is equal to in terms of understanding. So we say that a function Fn is theta of Gn if Fn is O of Gn. So that means Fn is less than or equal to Gn, and Gn, it's the other way around, it is true as well. I think there's a mistake here. So I'll just get to the next slide first. So again, omega notation, like I said, it is the opposite of big O notation. Opposite in the sense, we were talking about less than. Growth rate of a function is less than growth rate of another function. Now we are talking about when you have to say the growth rate of Fn is greater than the growth rate of Gn. So for function Gn, we define the omega notation as Fn is omega of Gn if there exist positive constants C and N0 such that for all n greater than N0, again we have that breakpoint after which this equation is true. Your Fn, if you see, 0 is less than or equal to C into Gn, which is less than or equal to Fn, which means Fn is greater than or equal to C into Gn. So this means that the omega of Gn is the set of all functions whose rate of growth is either same or it is higher than that of Gn. So Gn is an asymptotic lower bound. I'll just explain to you that in this graph. So now if you see, our equation is Fn is greater than or equal to C into Gn. That is, Fn is omega of Gn. That means Fn lies above Gn in the graph beyond the point n0. Okay, the constant is there. You'll see when we do examples why we have this constant. Constants don't make much of a difference to the actual function. They'll just shift them up and down in the graph a little bit. So all the functions that are greater than the yellow part that you see, everything that lies above Gn is obviously greater than Gn. Any function which lies in this range, and for any n0 for which it is always true, you can say that function is omega of Gn, means that function grows at a faster rate. And why is Gn called, if you see in this slide, it is called asymptotic lower bound. If you see, for the yellow part, Gn is the lower bound. So if you tell somebody that you are writing a program and its runtime will be omega of Gn, that means the runtime will always be greater than what Gn, it will, runtime will always be greater than. That's why you will not see we using omega notation to describe a function. You cannot tell somebody, the runtime of your program is going to be at least 10 seconds. So you're not telling him what is the maximum time it can go up to. You're just giving a lower bound. Say the lowest I can give you is 10 seconds. I cannot guarantee anything uh, where it will go, how much it can shoot up the runtime. So that's not a good way of telling somebody about the efficiency of your program. You're just giving him the uh, lower bound. But if you see, in case of big O notation, you are giving your Gn lies above. So you are telling that person that this is the maximum time your program can take to run for that particular input n that you're given. So your function time or your run time will lie within this yellow part, which is below Gn. So it is an asymptotic upper bound. And that's what we are looking for when we talk of efficiency of a program. We want to tell our customers, okay, this is the worst time that can happen. And if you're fine with running your program with this worst runtime, then it will be a good program for you. For example, when you are searching, if I tell you Google will take best case, it will give you the search results in 1 second. So worst case, it can give me in 5 minutes also. So that's not a good way of saying. But if I tell you, the worst time, that the maximum time it will take for you to search something on Google is 10 seconds. So which is a good way, because it's not always going to be 10 seconds. It's going to be lower than 10 seconds depending on what you are searching, where you are searching. So that is the way we describe. So mostly you'll see big O notation or theta. I'll come to theta after this. So we have to choose this C and N0, which will determine for sure that if for this constant greater than 0 and for N0, this equation will be true always. Okay. Now comes the theta notation. You'll see a lot of theta notation being used. So if you look at these two, I want you to look at these two graphs. So you see you have a Fn and you have a Gn, and the yellow part lies below Gn. If you see here, you have a Fn and a Gn. This time Fn is above this Gn. And in your previous case, Fn is below C into Gn. So now you look at the graph of theta notation. This is the graph of theta notation. So it is like a sandwich of both omega and big O notation. So I am telling, now I'm not giving you a upper bound or a lower bound. I'm giving you some kind of comparison that your function Fn is theta of Gn. That means if we go at the definition, so the definition says a function, all the functions that for some positive constant, there are two positive constants defined here. For any positive constants c1 and c2 and n0 is beyond this point, which point this equation will always be true, such that for all n greater than n0 we have this equation: 0 is less than or equal to c1 into gn, less than or equal to fn, less than or equal to c2 gn. So if you see, this is what it says. Your fn lies between, gn is a function, it will have one graph, but because of the two positive constants c1 and c2, the graph will shift up and down. So for two positive constants c1 and c2, if this is how c1 gn and c2 gn is plotted, your fn lies, the range, basically the values that your function will take will be between cn and c1 gn and c2 gn. So it is like, if you I have a comparison slide here. See, if you take a, if your c in the second and the third graph are different, if you overlap these two graphs, fn is the same, c1 gn is up and c2 gn is down. So sorry, c2 gn is up, c1 gn is down. Can you see my cursor, Amandeep, if I move it on the slide?
Yes.
Okay, so if you overlap these two, the omega and the big O1, you will get like when you overlap two sets, this is the common, what is it? It is not the union, okay, it's not the union. So your Fn, so what does it say? If you look at only C1, Gn and Fn, so Fn is greater than Gn, so Fn is omega of Gn. And if you look at, forget about the C1 Gn, Fn is O of Gn. So Fn is both, when Fn is O of Gn and Fn is omega of Gn, you can say that Fn is theta of Gn. So it is equal to. So when I say equal to, if you look at the graph, it is not equal to in the sense the mathematical equating two numbers. Equal to in the sense that it is in a range of values of Gn for some constants C1 and C2. So this is the formal definition. So if you see, look at this example, 10n square minus 3n, we say it is theta of n square. Okay, I'll just use the whiteboard to explain this. So your Fn is 10n square plus 3n. Okay. So it says it is theta of n square. So just like we did last time, initially for basic understanding, just make a table with different values of n. You make one more column, let's say 10 to the power 4. This is 10 to the power 8. This is 10 to the power 9. 3 into 10 to the power 4. So that is 1, 2, 3, 4, 3, 4, 5, 9. I think this is it. So what I've done is for different values of n, I am calculating the value of this equation. Okay. So if you see, look at these two columns here, 10n square plus 3n. If you are writing a program where one of your loops takes the time 10n square, and there's another loop that takes the time 3n. Okay. Now you look at the value as n increases, where does your program spend most of its time? If you look at, let's say, look at this column where n is 100. When n is 100, the time it takes for this 10n square loop, it obviously it will be a loop, it's n square time. It is 1 lakh units of time, right? And how long does it take to run the loop which has the runtime 3n? It is 300, right? So if I tell you to go and increase the efficiency of the program, revisit your code and see what you can improve, which loop will you go to fix the problem? Where are you spending most of the time in the program? You're spending most of the time in that part of the code for which the runtime is 10n square. You're not spending as against 1 lakh units of time, you're just using 300 units of time in the other for loop. So even if you go and fix that for loop, and for that 3n, if let's say if you reduce the time to 1, for example, your runtime is still going to be 1, 2, 3, 4. This is going to be a runtime. So you have not done any considerable improvement. It is still 1 lakh units of time. So what I want you to tell is your program is spending most of the time in this place, wherever this runtime is coming from. So that is where you want to go and fix the problem rather than worry about this 3n. So 3n is, when you look at this 1 lakh 300 and 1 lakh 1, this 300 is negligible compared to your 1 lakh units of time. So if you can get this 1 lakh down to 50,000, that is a considerable difference or considerable improvement in your program. So whenever you have, for larger values of n, your lower order terms, which is your this 3n, it does not play a major role in defining the time taken by the program to run. So when we say that we say that we ignore the lower order terms. So your program runtime will be defined by the highest power in your equation of that runtime equation of for that program. So what is the highest power here? It is n square. You are spending most of the time in the program in this part. So this is, if you have to go down and let's say revisit your code and increase the efficiency, this is where you should go, because this takes the majority of the time. That is why we say that this, I'll tell you why it is theta, but we say that the runtime of this program is n square. So we ignore the lower order terms and we concentrate on the higher order terms. Okay. So it is theta. Why is it theta of n square? Now, why is it theta? Why is it not O? Okay. So let's erase this part. So why is it theta and why is it not? So if it is theta, the definition of theta says what? It says that if Fn is theta of n square is your Gn, right? Theta, Fn is theta of Gn. So which means Fn is O of n square and Fn is omega of n square. And what would that mean? That means in terms of the how we equate, I'm just writing just to understand what big O and omega means. So Fn is less than n square and Fn is also greater than n square. But if you look at the definition of theta, we don't say it is, when it is O, it is some constant into n square and again some positive constant into n square, then this equation will be true. Okay, so I just rub off this part. I'll just leave the last line there. Okay, so according to the definition, if Fn is theta of n square, Fn is less than or equal to C1 into n square, and Fn is greater than, it is true for both. What is your Fn? Okay. Okay. Now, do you think these two equations are correct? For what value of C1 will this equation be correct? Okay. So, if, for example, if your C1 is 10, for example, so you are equating 10n square plus 3n less than or equal to 10n square. So, which is not true because you have this extra 3n on the left hand side. So, if C1 is 11, for example, will this equation be true? So do you think it is true? It cannot be true. If your n is 3, so you have 10 into, I just write n square because what is this? 3 into 3 is 3 square, which is basically in this case, since n is 3, this is n square, just replacement. So 10n square plus n square is 11n square is less than or equal to 11n square. Now if n is 4, okay, I'll continue this one on this side. So this is true. The equation is true if n is equal to 3 and C1 is 11. Okay. If n is equal to 4, I'm just looking at this equation currently. So I have, what is 10 into 4? 10 into 4 square. 10 into 4 square plus 12 less than or equal to, let's keep C1 as 11 only, and n square is 4 square. I'll just calculate this value. 160 plus 12, and this is 16 into 11 is 176. So 172 is less than or equal to 176. Right? So again, your equation holds true if your C1 is 11. Now if we do it for n equal to 5, so I'll get, this is 25, I'll get 250 plus 15, and this will be 25 into 1. So 265 is less than or equal to 265. Again, correct. So again, if n is 6, just giving you some examples. If n is 6, this is 360. and this is 18. 11 into 36. So 36 ones are 36, 36. I think this is 275. 25 ones are 25. Yeah, 275. So 36 ones are 36 and 36 ones are 36, 39. 396 and this is 18. 378. So you see, because you have n square on the right hand side, any value of n beyond 3 will not be, won't be n square at this position. So you will not get 11n square on the left hand side. You will obviously get something less than 11n square. So for n0 equal to 3 and for C1 equal to 11, your Fn is less than, or it is O of n square, right? So we have proved one part of the equation. The other part of the equation is that your 10n square plus 3n, we have to prove it is greater than or equal to C2n square. So let me just clear this. So 10n square plus 3n, to prove it is theta, that means the left hand side should always be greater than the right hand side. So let's say I select C2 as 1. It has to be a positive constant. So sorry, so the least I can select is 1. Is this equation true? So n, if let's say if n is 0, then if n is 0, 0 is greater than or equal to 0, it is true. If n is 1, 13 is greater than or equal to 1. If n is 2, 46 is greater than or equal to 4. So it's always going to be true, because if you see beyond 0, the left hand side would always be greater than the right hand side. But for C2 equal to 1 and n is equal to n0, which is equal to 0. Okay. Just have to check if n naught also has to be a greater than 0 or not. But in any case, for 1 and onwards, it is true. So your Fn is, for some constant C1 and C2, your Fn is greater than as well as less than. So we are looking at, let's go back to the presentation. Stop this share. So if we are looking at this here, you have Fn. That means when you choose C1 and C2 carefully, Fn will lie in the range between this yellow in the first graph. Okay, so it is both less than or greater than, but depending on constants C1, C2 and your N0. Okay, N should be greater than N0 in order restriction. So like if you see the third line here, it says what constants will work. You have to choose C1 and C2. How will you choose? You choose C1 a little smaller than the leading coefficient and C2 a little bigger. For example, we used for 10n square on the right hand side, we used 11 for the constant, so that we get a higher number on the right hand side. So that is why, why this function Fn is theta of n square. So we discussed why it is n square, why we are dropping off lower order terms, because when n increases, the lower order terms do not affect the runtime as much as the higher order terms. So we always focus on the higher order terms. And why it is theta? Because you can, using constant C1 and C2, you can adjust the function fn such that it lies between gn multiplied by two different constants, C1 and C2. So you are giving a range of values. So it is, when we say theta means equal to, it doesn't mean equal to, it means it is in between these two values. So you can say it is theta. We write equal to only to remember that when it's like when A is less than B and B is less than or equal to B and B is less than or equal to A is equal to B. It is like that, but not exactly numerically with respect to numbers. It is with respect to the mathematical functions. Okay, so if you remember, your bubble sort takes n square time in the worst case. Why worst case? Because if the elements are already sorted, then if you use that flag option, you can exit the loop right away at the first after the first iteration. So then bubble sort will not take n square time, but worst case it will take n square time. So whenever you look for an algorithm, you calculate the runtime like that. So we studied many sorting algorithms. Merge sort, quick sort have a runtime of, best case runtime of n log n. Merge sort is n log n. Quick sort has different runtimes based on how it works. We'll see that later. Now, if you look at this, the second line here, it says any sorting algorithm must look at each item at least once. So even if it's a bubble sort and you scan through the entire list and you find that they are already in order, how do you find that? You put that flag. If there is a swap, then they are not in order. If there is no swap in the first go itself, that means it is already sorted. But you still went through each item at least once. So that is why it says that any sorting algorithm is omega of n. What is omega? It is greater than. So any sorting algorithm will at least take the time to scan each element once. If there are n elements, that it will take n units of time to scan. So if it's the best case of bubble sort, it is already sorted, but it will still scan it once. So omega of n, it is greater than n. So you will not find any sorting algorithm with a runtime which is less than n. So for merge sort, quick, it is n log n into some other factor. Okay. Now another equation example. If you have a polynomial equation like this, you just straight away cross off all the lower order terms and just take it equal to theta of n cube. So if you see, there are four terms in the equation: 8n cubed plus 5n squared plus 3n plus 1. So your 3n is theta of n, right? Then it reduces when you have 5n square and theta of n. N is negligible compared to n square, so you make it theta of n square. But when you have n cube as well as n square, you make it theta of n cube, and you can adjust it based on, when you say it is theta of n cube, you are saying for some constants c1 and c2, and for n greater than n0, if 0 is less than or equal to c1 into n cube, that is less than your basic function, that is less than c2 into n cube, then this is true. Okay, so theta itself says that you are choosing two constants c1 and c2, positive constants, and then you are able to say this. Then, so these are the basic three notations out of big O, omega, and theta. Theta and omega are the one, theta and big O are the ones that you'll be mostly using to describe your runtimes for algorithms. Now, for information's sake, you'll come across small o notation. It is nothing but the same definition of big O with there is no less than equal to. Okay. Before I go into this limit thing, I want to show this omega. Again, omega is Fn is greater than Gn. So that's why Fn is omega, small omega of Gn. Okay. So I'll tell you what this limit is. So if you're given two functions and you want to find the relation between the two, normally we study the algorithm, we find, just a second, this, okay, I'll come. So if you are, we usually study a program and find its runtime and then compare it with the mathematical function and determine whether it's big O or theta or omega. Okay, but if you are given two functions, two different functions, let's say I give you n square and n cube, and I tell you, okay, tell me which one grows faster. This is the easy one. You can say n cube grows faster than n square. Then, but how do you find it in a sense mathematically prove it? So for that we use limits. So if, let's look at the main one, your Fn is big O of Gn if Fn is less than or equal to Gn. Okay, so if you look at this second definition here, if limit n tends to infinity, Fn divided by Gn is less than infinity, then it is O of n. And if it is, just a second, okay, then it is big O of n. And if it is 0, then it is small o of n. So if you look here, limit fn by gn, n tends to infinity is 0. So for two functions that are related to each other using the small o notation, the limit equation should be true like this. So fn becomes insignificant related to gn and as n approaches infinity. This is what it means. So this means gn is an upper bound. So let me just show you by one example. Just a second. So let's take any two functions. I give you the example of n cube and n square. So what is limit n tends to infinity n cube by n square, or limit n tends to infinity n square by n cube? So this one is n tends to infinity. If you divide, you get n, and here you get 1 by n. In case of 1 by n, 1 by infinity is 0. So you can say n square is O of small o of n cube. So that means n square is less than n cube. So the only place where n square is, if n is equal to, the only place where n square is equal to n cube is when n is equal to 1. So this will be true for n greater than 1. Okay, on this side, this itself is infinity. So if we go here and see, for big O, for n tends to infinity, if it is less than infinity, then it is big O of Gn. So we'll do some more examples of this one once we do the mathematical part. I want to do some more examples like that theta one. as well as for this omega and big O. So let's do that in the next class. Do you have a class after this, Amandeep?
Ma'am, at 2 p.m.
Okay, so I'll just take 10 more. I just want to finish this one and then we'll do the rest in the next class. So for you to remember, this is the relationship that you have. Okay, and limits part we'll do with examples. So I just skip this one. Now, what I want to go over is the properties of these asymptotic notations. Just like when you have a set, you define some properties like reflexivity, associativity, transitivity. Will apply to these mathematical functions as well. So if a function is theta of gn and gn is theta of some other function hn, then fn is also theta of hn. So this is called the transitivity property and it applies to all the 5 asymptotic notations. Reflexivity is a function is theta of itself, a function is omega of itself, a function is big O of itself. Then symmetry is that if Fn is theta of Gn, then if and only if Gn is theta of Fn. Okay. Similarly, Fn is O of Gn if and only if Gn is omega. So Fn is less than or equal to Gn if Gn is greater than or equal to Fn, which makes sense, and the same applies for small o and small omega. Then there are some terminologies that they use. Fn is monotonically increasing if m is less than n, then fm is also less than fn, and the same goes the other way around for decreasing. You just have to read through them. They're very simple ones. A function is strictly increasing if for m less than n, fm is also less than fn, and so the same for this decreasing. Then you also have to go over, because we'll be solving recurrence equations, so you have to go over basic formulas. Some basic formulas I'm sure you are aware of. Limit of, when you calculate the limit, if it's 0, then this function at the numerator is small o of function at the denominator. Then you also have to go over the log simple equations. The log that we use here mostly is log to the base 2. So natural log is ln, which is log a to the base e. A binary log is log a to the base 2. So some basic log equations like this. If you have log a, b, that is log a plus log b. Log, this one is important, log a to the base b, the fourth one, is log a to, if you have to change base, log a to the base c and log b to the base c. So, and all these, just go over them, I'll mail you. I'll just create a Google Classroom. Then again, to change base, this is the same formula. You'll see in many places, mostly we'll use log to the base 2. Then this let's do it after we do some practical problems. Summations, you will also have to go over the sum of some series. Linear series is sum of first n numbers, sum of first n squares, sum of first n cubes, then the geometric series. So this one is important, used at many places. The sum of geometric progression where your the what do you call that, r is not 1. So if you see, it goes from 1 to x raised to power n, which is basically x to the power 0 to x to the power n. So there are n plus 1 terms. That's why you have x to the power n plus 1 minus 1 by x minus 1. And if it's infinite series, then it is 1 by x. Okay, so maybe we might need some more. Mostly these are the summations we need. We need them in solving recurrence equations. I haven't gotten there, so we'll first finish how more examples like this one we did. How do we find, or how do we there are some rules, like for polynomial expressions you ignore the lower order terms and you find straight away, you can say that this is the runtime is theta n square, and how we justified using one example. So I'll try and do some more examples in the next class, and then we'll go on to solving recurrence equations, and that is the most of the mathematical part that you need. After that, we'll straight away jump to our different types of algorithms, starting from divide and conquer, since we have just finished merge sort, quick sort, and data structures. So it'll be quicker to finish that off first, and then we'll move to other algorithms. Okay. So if you have any questions, then you can email me, or you can just communicate to the CR. And if some things are not clear, I'll try. I am yet to get my original notes. I don't know in what shape they are. I'd given them to somebody. So whichever ones are in good shape and understandable, I will just send you PDFs like last time. But I'll also be sending you some online materials which I find easy to read or which relate more to the class. There's a lot of material available, obviously, but then you don't know what to skip and what to read. So I want you to follow whatever we do in class, follow that mostly for understanding, and then after you're done, then you can move on to do some higher if you want to read. I will send these presentations are not like original presentations. I'm just going over many presentations, and I pick up those things which and the order in which I teach in class. So I am mixing 3-4 presentations which I find suitable and easy to understand for students. So I will be sharing these presentations. I'll create a Google class by this weekend, and I'll put everything there like last time. And once I get my notes back, I will also try and put, I have done a lot of mathematical examples on them, so I will try to put them there in the form of a PDF. Ebook, I actually got a mail yesterday, which you can buy some ebooks. They're very cheap, some of them, but I don't know. I'll see which books I can assure are good. Uh, you don't need to buy also, but if somebody is really interested in buying or reading an ebook, then I have to think. Most of the notes, what I follow is Corman, not for every lecture, but many of the problems, my notes, personal notes are from Corman for most of the topics. And for some topics, I follow some online pages and notes that I have downloaded some time back. I don't know whether you'll find them now or not. And a couple of random topics from 1-2 books here and there. So that's what I said. For those, I will try to send you most relevant and easy to read PDFs that I'll find online. So if you find something easy or some website easy to follow, you can do that. But just keep a track of what is going on in class and what order and what all has been covered. Then you can read it possibly from anywhere. Nowadays, that's not an issue. But book, I'll see what I have with me, and I'll update you accordingly. By weekend, I'll create the Google Classroom as well. Okay. So any other questions? Just let me know. Okay. Just you can communicate through the CR. Okay. Amandeep, please take a screenshot of.
Yes, ma'am. Ma'am, I have done that.
Okay. Then you just mail it to me.
Okay.
Okay. All right. Thank you. I'll see you in the next class.
Thank you, ma'am.